about local versus global stationary points, and just managed to give you a little bit of a headway on briefly. But I want to go through these couple of examples now, and then I think you've got your lesson on Wednesday as a double towards a PSMT. So Friday we'll have to finish this topic, which means we're effectively a lesson behind, but I don't think it'll be a big problem in the end. So let's just run through this quickly, and then I can give you some time. So we spoke briefly about the idea of local versus global, and the main thing I want to talk to you about today is when they might appear and when they might become important. The first thing is that they're typically most important when you're talking about context. So you'll often be referring to local versus global in a context, whereas not in a context, it won't matter so much because you'll talk about this being a maximum and minimum, but it won't matter whether it's within a domain or not as much. So here is a context. It's a profit function. Profit function. So it's explaining when and where profit's made. And it's got a set domain of 0 to 2000. Determine the maximal profit. So this is something I want to do just to remind you of the optimization process that you've seen before. So that's approximately what the function looks like. We want to determine this value here. That's our maximal profit. And we want to determine what that value is and for how many items we need to sell that will allow that value to occur. So I'm going to zoom into here and I'll show you how this is done, but hopefully you're pretty aware of how it's done anyway. So our function is x over 1000, x minus 2000, x plus 500. So our function is profit equals x over 1000, x minus 2000, x plus 500. Was that right? Everybody memorize that function? No? Okay, that's good. We're good. And there's a negative in the front. Yeah. So to determine the maximum point here, we need to derive this function, look at when the derivative equals 0. So there's only a few times that I've given you things this year where I'm saying this should follow from that. So if you're asked to optimize or find a maximum and minimum, that should immediately follow in your mind as derive and let the derivative equal 0. That has to be the case. That has to be the next step. That's what you need to be doing now. And that holds for anything that's instantaneous rate of change. So that is if you're finding maximum velocities as well in kinematics, then you are deriving displacement model to find the maximum. Also, maximum displacement would be deriving displacement to find when the velocity is 0. So to derive this, there's a couple of ways I could do it, but what I'm going to do is I'm going to expand it because that's going to be the easiest way. So it is a 3-part product rule, but I can see it's a pretty easy one to expand, so I'm not going to go into the product rule so much. So I'll leave the bit out the front and expand the brackets first. I get x squared, I get minus 2000 times x, and I get 500 times x, which gives me in total minus 1500 x, and then I get negative 2000 times 500, which gives me minus 1 million, I believe. There we go. And then I've got that multiplication of x over 1000 on the inside. So when I derive this, when I expand this, I get negative x cubed over 1000. And then I get a negative times a negative gives me positive 1.5 x squared, because the 1000, 1500 divide to give 1.5. And then I get positive 1000 x, because a million divided by 1000 is 1000. And you will probably, for a question like this, have one of these, so you can use that. And then I'm going to derive that and find when the derivative equals 0. So I'm going to determine p dash, which is negative 3x squared over 1000 plus 3x plus 1000. And I want to determine when p dash equals 0. So I always have this little throwaway line here, y dash p dash dy dx, whatever it is. Let p dash equal 0. And I get 0 equals negative 3. I'm going to rewrite this slightly differently so I can see with clarity my coefficients. Plus 3x plus 1000. And I'm going to have a quick look at that and recognise, yes, I could multiply everything by 1000. That won't exist. I'll end up with a much nicer quadratic to work with. But I'm still going to have the 3 in front of my x squared, and this is going to become a million. So realistically, this is not going to be something I'm going to find easy to factorise. So I'm not going to bother trying to factorise it. Instead, I'm just going to go straight to my quadratic formula. X is equal to negative 3 plus or minus the square root of 3 squared minus 4 times negative 3 over 1,000 times 1,000 all over 2 times a, which is negative 3 over 1,000. And I will just put that straight into my calculator to determine those values, although I know that that's going to be 9 plus 12. I'm going to get the square root of 21. If anybody'd like to check me, you're welcome to. I know that obviously I've got 2 turning points in this cubic if I go back up to my graph, and I really don't care much for this turning point. So I'm going to be finding the positive answer, and the positive answer will be when I treat this square root thing as a positive. So I'm going to do that immediately and not worry about the negative answer. Oh, actually, no, that's not necessarily true because there's a negative on the bottom. With my negative on the bottom, by doing the plus on top, I've ended up with this negative here, negative 263.76, or I haven't got one of yours, so you'd have a solution in your calculator quite quickly with a polynomial solver. Square root of 21, no. Negative 3 minus the square root of 21. That. Okay, or 1,263.76. So that's my X value that will provide my maximum profit. Determine the maximal profit. This is where I've got to go back and actually determine the maximal profit. Now, if I go back to this context, I don't know what X is. X might be the numbers of litres of orange juice I sell, in which case it's a continuous variable, and I could do 1,263.76 in my continuous variable, but I might also have to deal with a discrete variable. Might be that X is the number of t-shirts I sell, and I can only sell 1,263 or 1,264. You might have to go back and look at both of those and see which one gives you the most profit. So just read the context and make sure you understand whether you're dealing with discrete or continuous. That might be your last mark. That might be the high level mark that you need to work out. But now I'm going to assume it's continuous because there's no information given. And given that, it's reasonable for me to say that the profit is equal to this thing here. I've got to put it all into there. So it's negative 1263.76. If anybody wants to calculate while I'm doing this, you are welcome to. X, not X. 1263.76 minus 2,000 times 1263.76 plus 500, and that will be my maximal profit. And I'm expecting it to be reasonably large. We're dealing with thousands of stuff. There's things multiplied together, so I'm expecting it to be reasonably large. Are you doing that, Harvey? You're doing it, Reggie? Okay, cool. Then I won't bother. Yep. Okay, do you have 2 decimal points? Okay, it's a money thing, so 2 decimal points for a money thing. And I was expecting it to be large. If I do a quick calculation in my head, no, I've moved across. No, I haven't. It's right here. That's about 1.26. That's about 700 to 800. That's about 1,700. I mean, this is 1,000 times 1,000 right here, and a bit more. 1,000 times 1,000 is a million, so I'm expecting a bit more than a million. That's what I get. So it's always good to have a bit of an understanding of where you're heading as well. But there it is. That's the maximal profit for that one. Any questions on that? Maximize, minimize, optimize, drive the function, let the derivative equal 0, solve from there. Any takers on this question? What functions are likely to provide local but not global stationary points? There's one main one, and then there's a few others that might. Explain, give me another name. So what's the other name for that? Cubics, that's it. Yep, perfect. Cubics always look like this. So beware of cubics. That is the main one that's going to provide you minimal and maximal, but not global. So they'll have locals, but not globals. Whereas parabolas always give you a global, because it goes down, it hits that lowest point, then it goes back up. It never gets lower again. Any odd function polynomial. So, and in fact, to an extent, quartics as well. So cubics are definite. Quartics can look like this. So that might provide two global minimums, might provide two different minimums, in which case one of them's global and one of them's local. But this guy here, that's often going to be just local, that maximum. Or if it's flipped up, it'll be the minimum, etc. But if you've got any odd function, it'll always do this and then go off that way. So you're always going to get that local versus global. That's for polynomials. Standard periodic functions won't give you that. They'll always give you that maximum and minimum and never change. But if you get some weird and wonderful periodic functions, which we won't really study in math methods, but you might be playing with one right now for your PSMT, for example, you get ones that have varying amplitudes, and that might provide local against global. Sometimes you get exponential functions as well that do weird things if you've got them multiplied by a polynomial or something like that. So of the functions you have to deal with, cubics or higher order odd polynomials are your main problem. So just keep an eye on them. Here's example 4, and I've talked to you for a while. I'm going to put this up. This example, I've actually pulled, this is an example that we've used a lot in past assessment for the Math B course. So it's come up in a few exams after this topic, and it also comes up as a variation of this example has come up on one of the exemplars for math methods. So I'm going to give you maybe 10 minutes to have a crack at it. We did something quite similar to it earlier in this OneNote, so you can have a look at that as well if you want. So about 10 minutes, I reckon. So this is example 4. We're given a function, but we're given unknown a's and b's. Questions like this pop up all the time in the work that you'll do, and I almost guarantee there'll be something like this in your external exam, maybe with tangents, maybe without, but definitely with that a, b coefficients missing, simultaneous equation requirement, etc. So you know that the tangents at x equals 1 and x equals 3 have an equal gradient. You also know that x equals 3 is an x-intercept. So that gives you two pieces of information, and there are two unknown constants, so you can find those. Once you've found them, it says determine the location and nature of all stationary points. It's a cubic, there'll be two stationary points, and you can work out the nature of those. One will be maximum, one will be minimum. We'll go from there. So the first thing is that we know f of x equals x cubed plus ax squared plus bx, and we know therefore that f dash of x is equal to 3, board's frozen, I'll see what people are saying, got it, is equal to 3x squared plus 2ax plus b. That's our derivative. We get the gradient of a function at a point by using the derivative. So I've derived it, and that we know that m at x equals 1 is equal to m at x equals 3. That's given to us here. So I'll call that number 1. So I'm going to use that. F dash of 1 is equal to 3 plus 2a plus b, and f dash of 3 is equal to 3 times 3 squared plus 2a times 3 plus b, which I'll just do a quick simplification. 3 squared is 9 times 3 is 27. That's 27 plus 6a plus b, and I know that f dash of 1 equals f dash of 3, and so I can equate these and solve for a and b. So I get this. 3 plus 2a plus b is equal to 27 plus 6a plus b. I can't actually solve for a and b just yet, sorry, my lie. But we can simplify this down to our first equation of two simultaneous equations. Oh no, we can solve for a here, can't we? Well, this works nicely. So I'm going to just subtract 6a, and I'm going to subtract b in the same line. It gives me 3 minus 4a, and then the b's disappear, equals 27. And I'm going to subtract 3, gives me negative 4a equals 24. I'm going to divide by 4, and it gives me a equals negative 6. And if a is equal to negative 6, that's right, I don't know the gradients of those points, so I can't find b here. But I can go back to my f of x and use the fact that x equals 3 is an x-intercept. That means that x equals 3 will make f of x equals 0, or f of 3 equals 0. So f of x is equal to x cubed plus, well actually not plus, minus 6x squared plus bx. Is that right? Yep. And we know that f of 3 equals 0. This is piece of information number 2, which comes from here. And so we get f of 3 equals 3 cubed minus 6 times 3 squared plus b times 3, and that equals 0. And so I get 27 minus 6 times 50 times 9, which is 54, got ahead of myself, plus 3b equals 0. 3b equals 27, b equals 9. And therefore, f of x is equal to x cubed minus 6x squared plus 9x. That's the first half of the question. Does anybody have any questions on that? That's the unfamiliar bit. That's the bit where you had to take the information about the tangents you've never seen in the nat form before, as far as I'm aware, and the information about the x-intercepts combined with the tangents, which is new, and do something unfamiliar with it. Mathematically, not all that complex, but there's a lot of processes, so it would be in a complex section. The next bit, though, if you can get through that unfamiliar bit, the next bit is very familiar. It's what you've done a few times. You did a lot in term 3. And so for this bit, we're just determining the stationary points and the nature of the stationary points of a cubic. So in part 2, we do f dash of x again, which you already know, 3x squared minus 12x plus 9. Let f dash of x equals 0. That's where our stationary points will be. 0 is equal to 3x squared minus 12, so that should have an x on it, plus 9. I'm going to divide 3 by 3 because I know that unitary quadratics are much easier to work with, and I also know that each of these can be divided by 3, so that works. And I get 0 is equal to x squared minus 4x plus 3. I look closely at that. Usually when the coefficients and the constants are different by 1, I can definitely do something with it. And in this case, I can write it x minus 1 and x minus 3. Is that true? Yep, that's true. So therefore, x equals 1 or 3. The stationary points occur at x equals 1 or 3. And the nature of the stationary points are determined by testing f double dash. But before I do that, I need to actually work out the coordinates of the stationary points. So I need the y values as well, which is the most common thing to forget to do. At x equals 1, f of 1, which is the y value, is equal to 1 cubed minus 6 times 1 squared plus 9 times 1. And that's equal to 1 minus 6 is negative 5 plus 9 is 4. And at x equals 3, f of 3, I believe we already know, is equal to 0. This is given to us, isn't it? So therefore we have the coordinate 1, 4 is a turning point, and 3, 0, a turning point. And now I just do the f double dash of x. F dash of x is equal to 3x squared minus 12x plus 9. And therefore f double dash of x, second derivative, is 2 times 3 is not 9. 6x, 3x squared derives to give 6x minus 12. And at x equals 1, f double dash of x, or f double dash of 1, equals 6 minus 12, which equals -6. Therefore, we have a negative means we have a maximum. So this is a maximum. And at x equals 3, I already know it's going to have to be a minimum. I get 6 times 3 minus 12, which equals 6. Therefore, we have a minimum. And that's our answer. Now, I've rushed through that a little bit towards the end, so you just need to be aware that that's how quick it can go if you know the content quite well. You probably have twice as long as I've just taken the question to do it in the exam. So if you can get those processes down pat, you can actually gain time on these questions. But you have to know that thing again. Stationary points. Derive, let the derivative equal 0, find your x values. Find your y values using your original function, check the nature with the second derivative. And they're all, like, there's 5 processes, hence complex question, but very doable if you know the process, which you'll know by practicing a lot of questions. Are there any questions?